Hello, welcome students, welcome to Helm of Science. Today we are going to learn a new chapter, the electric flask and corresponding the Gauss theorem. Let's start. In the last video, we have discussed about the electric line of forces and the electric charges and the corresponding Coulomb's law of electric charge and electric force. So, we are here today with the new topic is electric flask and the corresponding Gauss's theorem. So at the starting of this class we will have a basic idea about the area vector. This term will play an important role in learning of this chapter. Suppose there is an arbitrary volume. This is S. This is a closed surface volume. Okay, closed volume, and we take a little area ds, and this ds, the area is taken as vector. The area is taken as vector and the direction of this vector is perpendicular to this. That is, if we take it the direction in, it is always normally in normal direction with this area, and ds is the infinitesimal, the smallest possible area of this surface. And we have to remember this, the direction is always outward of surface with perpendicular direction, right? Now we have to know what is electric flask. So electric flask is nothing but the number of magnetic line of forces passing through a surface perpendicularly. So a number of electric line of forces passing through a surface perpendicularly. Suppose it is a surface of a box, cubical box or whatever, and a charge is present inside a box. So we consider a surface this ds. So the line of force from a point charge is in every direction, in three-dimensional every possible direction. So the line of forces will go out like this. From this box will go out like this, and maybe like this, or could be like this, and this is E in its every direction. So there must be some electric line of force which are passing perpendicularly from or through this surface ds. So the number of line of force passing through this surface perpendicularly is the flask. Perpendicular line of force is flask. and the flask is denoted by a sign called phi. So this is our flask. So a question could arise in your mind that if I take a surface here like this, so the flask or the line of forces from this position or from this area, suppose this is another this is ds1, from this area is not perpendicular, not perpendicular. So is there any flask present or not? We will measure that. There is a flask. There is a calculation to calculate the flask in any kind of arbitrary shape, arbitrary electric field or whatever. But for convenience or for simple cases, we always take the uniform electric field. Which is E, electric field or strength of the field. Okay. Now suppose this is a electric field of strength E. This is known as electric field strength or electric field, whatever. This is denoted by E, and there is a surface like this, and our test surface is this. This is ds, and the total surface is S. So as we learned earlier, the area vector, its direction is always outward or perpendicular of the surface. So this is the direction of S, and the direction of E at this point will be like this. This is the direction of E. So the angle, it's clearly visible that the angle is not the 90 degree. There forms an angle theta, let's say. So could you calculate the flask? Yes, we can calculate the flask. So what is it? So flask through ds is what? Nothing but denoted by phi is E dot ds. E dot ds. This is the flask. So from the concept of vector algebra, dot could be removed, as if we multiply with cos theta. Theta is the angle, and this could be written as E cos theta ds and or En ds, where En is the normal component of E, that is the electric field. So this is our desired flask through ds. And it has a unit. Let's calculate the unit. Okay, let's calculate the unit. What is the unit? Here is E. E means what we learned in the previous class is E is F by Q. Do it here, and we will consider the SI case only. E is F by Q, So the F is Newton Coulomb inverse. And there is another quantity ds, which is our area. So ds is area, and the unit of area is meter square. So the unit of flask is Newton meter square Coulomb inverse in CGS, or there is another, that is volt per meter. Okay, the unit of flask. So you can think that the electric field is passing through this direction like this, and entering in this direction, and at the point of contact, here the angle is different, here the angle is different, here the angle is also different. So what would be the total flask through this surface? We are calculating, considering a small amount ds. So what would be the total flask through this surface? So we have taken ds, that is the smallest possible surface. So flask through the, therefore flask through the total surface we will integrate this quantity. This is phi is equal to, suppose this is phi ds. So this is phi integration E dot ds, and the integration limitation would be over the all surface S. This is our total surface S, and we can write it removing the dot sign, E dot n ds over the whole surface. So this is interesting, and we have to remember one thing, that is at this, suppose this is a fictitious plane. Before this plane, the left side of this plane, the electric field is entering the surface, and the right side of this plane, the electric field is outward of this circle, is leaving this surface. So when E going out and when E going in, when E is going out, flask is positive, and when E is going in, flask is negative. You have to just change the sign of your result value of phi. That's all. Now we are going to discuss the Gauss's law of electrostatics. First of all, this is not a law, this is a theorem. Depending on this theorem, we will solve the another theorem or another laws of electrostatics. So that's why it is called the theorem. And the Gauss term is pronounced somewhere Gauss and also Gauss. So which one is convenient for you, you can pronounce that. So let's start. So according to Gauss's theorem, we will define the theorem now. Okay. So what is the theorem? So whenever there is a closed surface is and there is electric field going inside and also outside, and we will consider a small amount of area ds. Due to this electric field, the volume, the total surface area will get some charge. So there will be some enclosed charge inside this surface due to this presence of this electric field. So the total electrical charge, so our the theorem is total electric flask passing through a surface is equal to the one by epsilon times of charge enclosed by that surface. So this is our definition. So according to the definition, total flask passing through a surface is E dot ds, and this will be equal to 1 by epsilon times of total charge enclosed by that surface. So this is our mathematical form of Gauss theorem, and this is the integral form, and this is also the SI form. In CGS, the 1 by epsilon will be changed, and this would be phi is E dot ds on the surface is 4 pi by k into q enclosed. This is CGS form, and it's not so difficult. So and now suppose there is only one electric field present, and if there is a multiple electric field, like there are many electric charges are there, that is q1, q2, q3, q4 and dot dot dot. So the total electric flask, or the Gauss's theorem, will nothing but phi is equal to E dot ds, and E total means E1, E2, E3 up to En ds, and due to this E there, and it will be equal to 1 by epsilon times of q1, q2, q3 up to qn. So 1 by epsilon times of q total. So this is the simple formula for multiple charges. Now we will discuss some applications of Gauss's theorem. So as I mentioned earlier, that this is called the theorem because it will help us to calculate the electric field intensity or electric field strength at some point due to an arbitrary shape, or due to some multiple charges, or whatever, due to some presence of field. The application is, suppose there is a point charge and you have to calculate the electric field strength at a distance r from this point charge, or there is, suppose, wire, current conducting wire. There will be electric field due to this electric current conducting wire at some point. So there could be a spherical shell, metallic shell or non-metallic shell, both cases different. We can calculate the electric charge inside and outside of this shell. Suppose there is a metal sheet like this. This is complicated, but this metal sheet is charged, somehow charged. So we can calculate electric field due to this metal sheet at some distance q, or at some distance r or r1 or whatever. So this is the application of Gauss's theorem. So we will consider the simplest case, that is application number 1. This is the simplest case, that is the E due to, E means, I am not writing it in detail, electric field intensity due to a point charge at a distance. So it is mentioned that due to a point charge. So first we will consider a point charge. Suppose this is q and the distance, suppose at r distance from this q. This is our test position. So at first, what will we do? We will draw a circle of radius r centering the q, and this circle would be the Gaussian plane. We have to consider a Gaussian plane every time when we are calculating the electric field strength for any kind of charge distribution at some distance using Gauss theorem. So according to the Gauss theorem, at some point, and we are considering area vector ds here, and there will be electric flux outwards of this area, and as we have considered a circle over here, the radius of the circle is everywhere is equal. So on this surface of this sphere, the electric field strength will be equal. We can assume that, we can say that. So electric field intensity phi electric plus phi through this surface is equal to E dot ds, and it is equal to the total charge enclosed by epsilon and it is written as E cos theta ds is equal to q by epsilon, and from we can say that the electric field is outward of this smallest area vector, and it is outward perpendicularly outward respective to this the direction of area vector is at this direction, and the electric field due to this charge is also this direction. So theta is 0 degree. Both the direction of electric field, and that is E and ds, is 0 degree. So cos 0 is equal to 1. So this is E ds is equal to q by epsilon. And as E is uniform, we have mentioned earlier that E is uniform, so we can pull it out from the integration, and ds is equal to q by epsilon, and E and ds is the surface element or surface vector, and if we integrate all over the sphere, the surface area of the sphere is 4 pi r square. We are integrating the ds all over the s, that is the 4 pi r square is equal to q by epsilon. So E becomes 1 by 4 pi epsilon q by r square. So E becomes 1 by 4 pi epsilon into q by r square. So this is a required electric field strength, electric field strength or electric field intensity for a point charge at a distance r. Now we will see another application of Gauss's theorem, that is number 2 theorem. It is the electric field intensity due to a charged thin spherical shell. So in this case we will take a spherical at first we are going to calculate the electric field intensity at some point due to the spherical shell if the test point is outside of our shell. Suppose there is a spherical shell, it is outside, and we will do here the inside. So suppose this is our spherical shell, it is charged with a positive charge q left. So as this is a spherical conducting shell, the charge will be distributed over the surface here, and our test charge or test point is here from distance x. Suppose this is P and this is our center O. The radius of the sphere is r. So according to the Gauss's theorem, we can say that E dot ds is equal to, for the surface S, E dot ds is equal to q by epsilon. Our charge is q, and and here is the main trick, that is we have to consider our Gaussian surface this. I will use a different color here for your convenience. We will consider the Gaussian surface. this is the Gaussian surface. We will calculate our electric field along or with the help of this surface. So the ds, this is our ds, and this is radially outward, and the electric field due to the charged sphere is also radially outward, so both are parallel. So E dot ds is, you can write it, ds is the total surface area 4 pi x square, that is the distance from center to the test point P, is equals q by epsilon. So E is equal to 1 by 4 pi epsilon q by x square. And now for this case, suppose this is our sphere, it is charged with charge q, this is the radius r. Now inside we have to calculate charge at here, suppose this is p prime. So the main funda is to assume the Gaussian surface. The Gaussian surface will be a sphere whose distance will be whose radius will be the distance from the test position to the center. And as we know that the charge is always distributed over the surface of the cell or the conducting cell, so there is no charge inside or no electric field inside the spherical shell. So E dot 4 pi x prime square is equal to 0. Why 0? If q inside is 0. So E is equal to 0. This is the very important to remember this formula or this method, or these two formula actually. This is very important in joint entrance and competitive. They always ask some tricky questions where you have to calculate the electric field intensity inside a spherical shell. So it is always 0, remember this. Our next application would be number 3, that is electric field intensity due to current carrying wire. Okay. And it is infinitely long charged. So assume where it is charged with Q. The Q charge per unit length. So if the total charge of if the total length is equal to L semi or whatever, so total charge Q into L. You have to remember. So suppose for this we have to calculate the electric field here. So what will you do? We will draw a imaginary line of distance, suppose r, and we will consider a cylindrical Gaussian surface for this arrangement, or for this straight wire. This is the distance r from this point to P. Suppose this is O point. Now this is our Gaussian surface. Okay. So according to the Gauss's theorem, E dot S is equal to total Q by epsilon. And now there is the two kind of surface in this picture. One is the plane surface over here and here, and another is the rounded surface. This the rounded surface. So we will distribute this like E ds cos 90 degree. I will do it elaborately. So E dot ds plus E dot ds. This is the plane, that is this plane and this plane, and this is the spherical body, the cylindrical body. Cylindrical is equal to, so Q total will be Q into L by epsilon. So for this plane here, the electric if we consider area vector like this is vector is directed upward and the electric field is in this direction. So the angle between is 90 degree, and cos 90 degree is equal to 0. So this will be become 0 for the planes, for the two planes, this and this, plus only this term will remain, that is the cylindrical part, because the ds and the E are both parallel. So cos 0 degree is 1. So this will become E dot ds, and ds is the surface area of the cylinder, that is pi rl, 2 pi rl, 2 pi r into L. L is the length of the wire, is equal to Q dot L by epsilon. So this will be E equal to 1 by 2 pi epsilon into this L will be cancel, Q by R. This is our desired relation. Now we will go to our next application. Hope you are understanding well, and you will like our video, share and subscribe our channel for more subjects and more videos like this, and comment below, are you enjoying or not. and please comment your requirements or your questions or doubts in this comment section. We will try to solve your queries. So let's go to the number 4, that is the field intensity due to uniformly charged lamina. So what is a lamina? A lamina is nothing but a piece of metallic or non-metallic sheet which has a negligible width. Okay, so suppose this lamina is charged with charge q. You have to calculate here the field intensity. So at first what we will do is we will consider a cylindrical shape, and thus cylinder will pass through P, and in the negative side or in the opposite side we'll consider another cylinder which will be equal to this, and it will pass through P prime. And as the total charge will be the surface charge density into surface area. And the surface charge density is written as sigma, and surface area is ds as mentioned. So according to the theorem of Gauss or the Gauss's theorem, E dot ds is equal to q total by epsilon. And now here is a surface ds, here is another surface ds, and the electric field is going outward with respect to this lamina. So there are two, number one, number two, two kind of electric field which is getting outward from this lamina, and this will be 2 eds, and q total is sigma ds by epsilon. So E is sigma by 2 epsilon. Hope you have understood. This will be this, because here is EDS and here is another EDS. So this will become 2EDS, and the total charge is surface charge density is charge per unit area. This is sigma, and this is the surface charge density. This is okay. So sigma into total area is a considerable area is ds, and both sides ds will be cancelled, and our answer is this. And this is a non-conducting lamina. that is the charge will not going anywhere, it is distributed evenly all over the lamina. Now our next and the very last application or example is number 5. Infinite conducting slab. Previously we have discussed the lamina, that is the only sheet with a negligible width, and now we will just increase the width little bit like this. Just increase it, so this is our slab and it is charged with Q, and the charge will be evenly distributed over both sides the lamina. So again we have to calculate the electric field here and here. This is the midpoint of the slab, so we will just consider a cylinder over here which is passing through the point P, and here also we will consider a cylinder like this, and as this is not a lamina, this is a slab, so this is the width, okay, this is ds, the electric field is perpendicular to the plane of lamina E and parallel to ds. Here also E will be going outward, and surface charge density is sigma. So total charge is equal to sigma dot ds. Now we will apply the Gauss's theorem. So here is E and here is also another E, and two are different. This is number 1 and this is number 2. And this is number 1 and this is 2. So there is two different surface. So applying Gauss's theorem, 2E dot ds, and here comes a twist, that is this is a surface, this is surface 1 and this is surface 2. Please follow mindfully. This is surface 1 and this is surface 2. So there is two different surface. Here is one surface and this is the one surface. So there is sigma ds total charge, and here it is also sigma ds total charge. So the total charge will be 2 sigma ds, total charge of slab. So this will become dot ds is equal to 2 sigma ds by epsilon. So 2 cancel and ds is also cancelled. So E is equal to sigma by epsilon. This is our required electric field. So this is slab. And remember, for lamina it was E equal to sigma by 2 epsilon. So we can write, so remember the electric field intensity will be slab by 2 is equals lamina. This relation is very important. So this is our Gauss's theorem and its application. Hope you have enjoyed the video. Thank you so much.